start recording. So good afternoon, everyone who just came in. I have just recorded the video, and what you see in the slide, it's the proposed midterm exam date, which will be on Wednesday afternoon on 29th of September. I hope that's okay for you all. It's very important if you are unable to have the exam on this day and time, just let me know as soon as possible, because I will start arranging all the invigilators and you know, I need some people to help me for invigilating for you to have an exam. We will probably use Zoom and along with the My Course View system, and we might use Discord as well. Okay. So I hope you can hear me okay, clear enough, yeah? No noise. Do you think it's better than last week, the voice? No one said anything. But if you think, that there's some noise, sound, or anything, just let me know. Don't you know? Don't let it have noise or something like that. Just let me know. So I'm trying to change something. So one of your friends said there's no different for you. Okay, that's good. That's good. Okay. Okay, so we'll wait for your friend for a little bit more. So today we have one more topic left from last week. And before we continue to the next topic, so for last week, I have introduced the conversion between the spatial domain of an image and the frequency domain. So I hope that you'll be able to analyze an image in frequency domain. You know that I wouldn't go through in too much detail of the technique to use, but we call it Fourier transform, and because we work in a discrete domain, so we use discrete Fourier transform, and we can invert the Fourier transform back. Maybe I should write something like this. We can transform using discrete Fourier transform, and we can invert this back using invert Fourier transform. And what you've seen from the image, they are a complex number in an image. After you transform them, they are sort of all the complex. So if you want to take a look at the spectrum, you will use the calculation to see the spectrum, which I have provide the formula in the slide, in the previous slide, and you'll be able to find the magnitude of the complex number. Like you know that you use like the root mean square, the sum of square of the real components and the imaginary components. So once you have applied the Fourier transform on the image, you get another image in frequency domains. And I have told you that you'll get the starting point of the frequency domain on the top left of the image. But because of the properties of the Fourier transform, you should shift the center to, you should shift the origins of the frequency domain to the image center. And what you have seen is, you will see that the whole image is all conjugate symmetries. You will see all the spectrum like all over, and they are symmetry, you know, in when you move the origin to the center of the image. So first, and I have talked about the low frequency and the high frequency. And now you all probably know that when I have shifted the origins of the frequency image to image center, for here we would call it the DC component. And around here would be ranging from low frequency to high frequency, right? To high frequency. So around the origins, there will be low frequency. And outside, you'll see the high frequency. So today, what we are doing is we are going to work on filtering. We are going to filter an image in frequency domain. To basically, we would just separate an image between low frequency and high frequency, and we will see what it's actually look like, the image in low frequency and the high frequency. So I hope you kind of remember, try to revise a little bit from last week. But if you have some question, you can, pop in some question in the chat, or you can turn on your microphone and ask me. All right, so yeah, basically you shift the origin and you get the low frequency and the high frequency. And now we're going to filter them. So in this picture, I sort of, imitate how we filtering. We have a number of frequency and we filter some frequency out from the filter. Okay, so let's continue. So in this section, I will talk about the three different types of filters. Three different types of filters. We call it ideal filter, the Butterworth, and the Gaussian filter, which could have different results when we filter an image. And so the application, I have divided into main application. First, we will talk about the low pass filter. And second, I will talk about the high pass filter. So at the end of this topic, you will probably see, oh, what is the low frequency of the image look like when we using high pass filter, and what is actually look like for the high frequency image when we take the frequency domain image past the high pass filters. So here the process for filtering. Here is actually the process for filtering. So what you will do is you will start with the original image here. You start with the original image here. You might want to do some pre-processing, but yeah, you might not have to do it. But then we want to do some filtering. We will pass it through the Fourier transform to get the F, U, and V. And X and Y is in spatial coordinate, right? The X and Y. the spatial coordinate, the pixel location. But for the U and the V, it's actually the frequency in, for U, it's sort of the row direction, and V, it's sort of the frequency in the columns or vertical directions. So then we'll pass a filter. This filter, we can decide it whatever we want. And we're going to talk about the many type of the filter that we can decide. And what you do is you just apply the decided filter, multiply them with the Fourier transform of the original image. Basically, you just multiply them, and then you will get a filter version of image, but it's still in the frequency domain. So you have to pass the inverse Fourier transform to get the original image. Sorry, not to get the original image, to get the filter image. To get the filter image. And as you see that, they say that the image is enhanced. So the filtering process can be used for enhancing an image as well. But it might include some pre-processing and post-processing. But don't worry about this process. What we want to do is we want to work through the filtering process just here. We're going to focus on this process here. However, when we want to create a filter image, another thing that I would like to talk about it, and I have omit in here, is whenever you create a Fourier transform image, you probably want to move the origin to center, so you will be able to get the symmetry frequency value all over the image. So there a process of that. You have to shift the origin to the center as well. And what it has been said in here, that in the pre-processing, they have used the shifting property in Fourier transform that I think I have mentioned a little last week, that you can multiply the original image with -1 to the power of X position and Y position together. You will be able to automate it, shift the origin to the center. So there's another way you can do filtering. You can multiply the original image using this factor. And once you compute the Fourier transform, you automatically get the origin to the center of the Fourier image, like automatically. And then you can multiply it with your desired filter, and then you find the inverse versions to get the final enhance or the filter image. So basically, you can shift the origin in the spatial domain or the frequency domain. But what we are going to use in here, we are going to shift it in frequency domain. So, like I said, if you have a transform version of your own image and you have your design filter, you can create a filter image which is still in Fourier transform by this equation using simple multiplication. Very simple. How do you filter an image? Sometimes the HUV is also called a filter or the transfer function You might heard this word as well, but it's actually in the frequency domain. So we'll start with one type of the filter. The first type of the filter is actually the low pass filter. Like I said, when you shift the origin to center, here it's sort of a DC component, you get the low frequency here, and the high frequency around here. So for low pass, it means that you want low frequency to pass, from this filter. But for the high frequency, they will all be removed. The all high frequency will be removed. So how do you decide the low pass filter? So basically, if you want something to pass, right? If you want something to pass, you probably multiply, because you know that the formula is multiplication. So whatever multiply and you get like the same value, it must be the value of 1, right? The value of 1. So at the low frequency, we will probably want them to pass. So we will probably multiply them with number 1. Whereas the high frequency, we don't want them to pass through the filter. So we use 0. So whenever you multiply the 0 with anything, it will all be, removed. Or the frequency at the high frequency will be all removed. So this is actually this is actually a basic filter, which is called an ideal low pass filter. So I'll show you in the next slide. So this is actually the basic filter, which is called the low pass filter. You see that all the low frequency in here is all passing because they have the highest value, which could be equal to 1, because 1 multiply everything it will remain the same value. Whereas the high frequency here, you see the U and the V is actually the frequency in, horizontal direction and vertical direction. You see that all the high frequency, they all become 0. So you can write down the filter, or you can call it transfer function as well, in frequency domain like this. And you will let it pass for certain frequency, and we call this frequency is the cutoff frequency. So you can expand, or you can, decrease the cutoff frequency as you wish. And we will use this one, and we will apply it on an image for low pass filtering. And it's actually an ideal because it has been changed from 1 to 0 at, at the particular cutoff frequency. So that's why it's called an ideal low pass filter. Okay, there's some question. One of your friends asked, does it use the property of the convolution? Yeah, I was going to talk about it, but it will be, at the end of this topic. You actually spoil the class a little because that's a very good property of, that's very good property of the convolutions and the frequency filterings. I will point out the relationship between two of them later on, okay? Okay, I will talk about the convolution later on. Okay. So now we are working in frequency domain. We're now in frequency domain because you see the H is capital, and we also we're going to work with the image in frequency domain as well. So we're working in frequency domain. So let's see the next image. So this image is sort of a result from the low pass filter. Let's take a look at this image. So the first one is actually the original image, and you can see it very clear, I hope it's clear image, clear enough. And the 5 later image is sort of the result from ideal low pass filtering. And they have changed the cutoff frequency. They have changed cutoff frequency to many different cutoff frequency. For the first one, the cutoff frequency is very low at about 5. So when you have the filter here, the filter here, and you have a very low cutoff frequency, about maybe 5, about 5 pixels here. So what it means that you let a very small amount of the frequency pass through the filter, and the rest of the frequency will all be removed. So that's why what you see that the image is quite, very blurred, very blurry, because what it has actually been passed through the image, it's only small information here. The 0 small cutoff frequency, it shows the small information. That's why you see a very, very weak image, very unclear image. But then what they have do is they have increased the cutoff frequency to, larger, like 15, for example, like 15 pixels. So right now you can see a bit clearer from this one, and you can see some more detail. That's why that's how you add like a higher frequency components in an image, so you'll be able to see more clearly. So to be able to summarize from this image, the low frequency is sort of an overall image that you have seen, like overall image. But for the higher frequency, whenever you increase the size of the cutoff frequency, when you increase the size of the cutoff frequency, you will see clearer and clearer. That's why all the higher frequency information has been added to the image. And finally, when you get a very, large cutoff frequency, you will not see, anything unclear at all. So, it has enough information for your eyes to not be able to detect what has been missing or what has been filtered out already. So the cutoff frequency is some sort of tells you how many information you want it to be passed through the filter. So I hope you see, like, you get some more idea about the frequency in an image. So these are sort of a very low frequency, and you add a higher frequency, you nearly get the original image. And the circle is sort of your design cutoff frequency. And in exercise, I will let you design your own frequency as well, cutoff frequency. So for ideal low pass filter, what you have to identify is only just the cutoff frequency, and you'll be able to get, all the low frequency out from the image. Okay, this is the ideal low pass filter. So let's take a look at another low pass filter as well, but it's actually called a Butterworth low pass filter. The Butterworth low pass filter is actually trying to model the ideal low pass filter, but to be like smoother transition from the high value of the passing frequency to the stopping frequency. So you see what's so different from the Butterworth and the ideal filter is actually there are some transition. There's not just immediately change from 1 to 0. So it's gradually change from 1 to 0. So in here, we also have the cutoff frequency, D0 as well. D0 is sort of a cutoff frequency. And for the DUV, is actually the distance of the particular U and the V, positions of the frequency, and D it's sort of the distance from the center, So when you select some cutoff frequency, at the same cutoff frequency, for example, if DUV is actually equal to the cutoff frequency, in this component, you will get the value of 1. So your function would become 1 divided by 1 plus 1. So it's actually equal to 1.2 or 0.5. So whenever your frequency is at the cutoff frequency, the percentage of the passing percentage is about 50% here. Okay. So at the cutoff frequency, you will allow that frequency to be passed about 50% of them. So there are some removed and there are some passing. So what is actually said from the Butterworth is actually you will not, select some of the frequency and remove some of the frequency, but you select and give the weighting value, give a weight value for, for each frequency until they are not allowed to be, to be passed at all. So it's sort of, smoothly, gradually transition from 1 to 0. And there are also another parameter n as well. So if the parameter n is sort of increased, the parameter n is increased, you will see from the graph here. I'll change the color a little bit here. So I'll use the green color for parameter n. You see that if n is small, the n is small, the 2n, this component would be small as well. But if n is large, the divider would be large as well. So that's why the transition between passing frequency and stopping frequency is sort of, I think it's sort of slower moving from 1 to 0. So for Butterworth low pass filter, you can design them using the cutoff frequency D0. It means that how much of the information that you want them to pass through the filter, and you can also identify the the power here as well to be able to say that if your graph would be gradually changing or very quick changing. So there are 2 parameters that you can configure for the Butterworth low pass filter. So we'll see a little bit of the result in the next slide. Yeah. So whenever we increase the number of the end, you will see there are fluctuated value here. So it's mean that there are some component that they have been removed, and there are high frequency component that they're still include into the low pass filter. So they're not just like an ideal filter that they have changed from 1 to 0, but they sort of still keep some and remove some. So what you see from the Butterworth low pass filter, what you see in that the image just here on the right is same image, and the original image is sort of here as well. So when you the cutoff frequency of the order 2, it's mean n equal to 2. And the cutoff frequency has changed from 5. This one is 5. Maybe I should use the darker color. 5 and 15 and 30 and 80 and 230. So what you have noticed that similar to ideal filter, you'll see that if the cutoff frequency is very small, the information passing through the filter is not so much as well. But if you add more higher frequency around the radius, you will probably get more information. But what is actually different from Butterworth filter and the ideal low pass filter? What is actually different? Have you noticed? Have you noticed? The result from ideal low pass filter and the result from Butterworth low pass filter, do you see difference between them? Do you see any difference? Maybe it would be better if I, put the picture together, like maybe just here. Yeah, we are not talking about the Gaussian just yet, but yeah, we talk about Butterworth and the ideal low pass filter. You see the difference between them, the result. For the high frequency, it's quite similar. I mean, when the cutoff frequency are high, the results are quite similar. You don't see anything different. But when the cutoff frequency is sort of, smaller, you see that the image result from Butterworth low pass filter shows smoother, right? Smoother in texture compared to the ideal low pass filter. The reason is because the combination of frequency for us to see is not just low and high frequency, but they all combine between low and high frequency. So to use the smoother filter will show a smoother result, because this one is sort of changed from 1 to 0 immediately. So the result is sort of not so smooth compared to the Butterworth filter.
จ้าครับ
Yes.
What does the white part mean in the Butterworth low filter? Like the slide 57.
This one.
Before this one. Yes, this one. Like there are white circle in the middle, and they are like alternative. They are like alternate. The white part alternate.
Different of them, right? It's quite similar to the ideal filter, but for the ideal filter, all they have like a sharp circle in white color, right? But this one has a black color, and for this one, it's actually a Euro design low pass filter, HUV, which quite, which are not so sharp circle because of the shape of the design filter. You have seen that the value is gradually changed from 1 to 0, and 1 is sort of the white color, right? And 0 is sort of a black color. So this is sort of represent the filter in 2 dimension, or our HUV. Is that what your question is about?
Yes, yeah, got it now.
Okay, so that's why only the white area is actually allow the frequency to pass, and more white, more frequency passing, more white, more frequency passing. And for this one as well, there are white and alternating here. So there's some mixture of the frequency of the high and the low frequency. So there's sort of a design for the filter. Okay, the last one is Gaussian. Gaussian is very similar to Butterworth because the shape is sort of changing gradually from 1 to 0 to 0. And this one is actually how the Gaussian is look like. And you know the Gaussian that the Gaussian distribution is sort of a bell, right? And when we take a look at one side, we can, identify or the mean value and the variance, right? And the variance here, it's quite similar to how you look at D0. It's quite similar how you look at D0. So when D0 or the cutoff frequency, it's larger. When the cutoff frequency is larger, your bell or the Gaussian distribution is wider. Mm. Yeah. So yeah. So for the Gaussian filter, you have only D0 to decide which one of them you want them to pass through, the filter. So similar to Butterworth, this is the original image. And when you pass with the cutoff frequency, the cutoff frequency here is actually 5 again. So the information here is very little. So that's why you see a very weak image. And when you add some more frequency by expanding the cutoff frequency value, you get some more information or some more details into an image. Yeah. So that's are the examples of the filters. Okay, so this is the comparison. So the Gaussian and the Butterworth are not so much different in the result compared to the ideal filter. Your friend asking this slide 57. How can it become the minus? I think it's actually not minus. I think I have like, if you use this formula, right? If you use this formula, you calculate it using different cutoff frequency and different D and different N. I think you will not get the 0 value. I think it could be something like this, but the graph has show the value, reference value just here. Yeah, I think when you calculate it, it's not going to be minus. It's just a reference value that you can find that they looks different for different N. You can try it on Python. Yeah. Whether when you apply N equal to 20, will you, I suppose that you will not get the minus value. Yeah. But the value is sort of fluctuated. Okay. So I'll continue now if there are no other questions. So the next one is sort of a high pass filter. So high pass filter is sort of the inverse of the low pass filter. And for high pass filter, we want the frequency that passing through the filter, they are the higher frequency. So which frequency we want them to pass, we will assume, not assume, we will let them have one value, and the frequency that you don't want them to pass, it will be equal to zeros. That's why 0 is a black color and 1 is sort of a white color. So that's how it looks like in here. So here is sort of the ideal high pass filter, the ideal high pass filter. And how you calculate it, you just use 1 minus the transfer function in the low pass filter. Just 1 minus. So all the frequency here is the ideal low pass filter. When you minus it to 1, it becomes 0, becomes 0. But then all the 0, it become 1, right? So it's actually flipped. It's already flipped. So this formula is also applied for the Butterworth and also Gaussian filter as well. So these are the conditions for a high pass filter. For example, within cutoff frequency, the high pass filter, it's become 0 now because we don't want the low frequency to pass through the filter, whereas it's become 1 when the frequency are higher than the cutoff frequency. I think they sort of have the value. And here it's sort of low pass from, previous slides, and I copy it here. So in here and here, you can, use 1 minus the low pass filter to get the high pass filter for Butterworth and Gaussian filter as well. So these are the how you look in 3-dimensional high pass filter. You'll see that all the high frequency outside the cutoff frequency, they all will be multiplied to 1. So they all will be passing frequency. All high frequency is passing. But all the low frequency, they are removed immediately because they are ideal high pass filter. Whereas for the Butterworth and the Gaussians, they're quite smooth. So you're not removing the low frequency immediately, just gradually remove some of the low frequency, just like it here. And the same parameter that you can configure, for example, for Butterworth, I think you can use, you can configure the D0 and N, the order of the Butterworth filter. And for Gaussian, you can just select the variance of your Gaussian distributions using the cutoff frequency parameter. And what you've seen from the result for different cutoff frequency. In here now, because it's actually high pass filter. So if the cutoff frequency is small, if the cutoff frequency is small, it means that a lot of information has been passing through this filter. There are a lot of information passing through the filter. But if your cutoff frequency is large, so only small information will be passed through the filter, and they are all high frequency. They're all high frequency and smaller information. So you have seen that when we increase the cutoff frequency, the size of the cutoff frequency, the information is getting less and less. The information is getting less and less. There's some question. What are the different use case between 3 types? I wasn't really working on the high pass or low pass filter so much, but but mostly they're not really use ideal filter. They're not really use this one, but it's easy to, to understand and to understand the frequency component. So it's easy to learn, to study. But when they work in the real scenario, it will be better to use non-ideal filter, because it has been compromised between the removing frequency and the keeping or the passing frequency. So in real scenario, I have often seen the filter in this area more than the ideal filter. And there are actually some other filter as well. Some of your friends might heard about the Chevy shape filter, There are also another filter as well. And I haven't really worked on it so much, but it's just another type of filter. If you want to know more, probably you might have to take a look at the case that they really use. But yeah, in here we just show the smoothness of this filter that is more than the ideal filter. So then one of your friends asked about the exam. The exam will be theory or the command, like a programming command, right? I haven't decided yet. I haven't designed the exam just yet. Last year, we have separate into two different types. First is theory, and the second is an open book, and using I'll give you a problems and you solve the problem. So that's how last year has looked like. But most of it, there are sort of theory, because I'm trying to give you a programming work in homework. So I suppose that you'll be able to, to write a program to solve some problem or understand some to understand some knowledge in image processing.
ครับ
ค่ะ
can you explain the difference between the role again? I didn't quite
the role, right?
Yeah.
You mean this one, or I haven't talked about this one, and I think the role has been overlapping.
No,
role.
I mean, I mean like the picture and the picture on the left and the graph on the right. Like I'm confused how they are related. Yeah.
I think the image is quite overlap. Let me check these two. Just give me a second to check these two, just in case that they are different, because they look so much the same here. Let me check the original image. Well, there are actually some descriptions between all of them. And there one extra image that has been overlapped on this. So I will update the slide later then, because I think I forget to bring the description of this image. But let's take a look at one top row here. So I suppose that they have a different D. And different D. And I think they are different for the ideal and the butterword. Ideal and butterword. And another one is Gaussian. So the result is quite similar, right? But the butterword has been hidden here. So you will not be able to compare them so much. So there's no other image anymore. But yeah, so these are the result from the ideal filter, and I will update the image later. Let me, maybe I'll show it just here. For this one, maybe look better. So the top row would be a result from ideal filter corresponding to the shape or the look of the transfer function of the ideal high pass filter just here. And the second row would be high pass Butterworth, high pass Butterworth. And I think the last one is the Gaussian high pass. And they are choosing different cutoff frequencies, so they show different result. But in my thinking, they are not much different, but only when the cutoff frequency is small, you will see that the Butterworth and the Gaussian result quite show the smoother result compared to the ideal filter. So yeah, so top row corresponding ideal and Butterworth and Gaussian changing different cutoff frequency. Okay, so I'll update this picture for you.
So the rightest one would be blurrer than the leftist one, right? Because the cutoff frequency is high.
The cutoff frequency is high. It means that when the cutoff frequency or the circle here is really large, right? Cutoff frequency high. So the circle is really large. So you will see when the cutoff frequency is large, the black area will be large as well. The black area will be large as well. So the passing frequency will be only small, high information outside the circle. So that's why the information that came out from the larger cutoff frequency show very small information. Does that make sense for you? So when the cutoff frequency is really large, or here it's become black, so only the passing frequency information is only small area here. It's only small area here. So that's why the information here it's very, very little. And it tells you that these are all the high frequency. These are all the high frequency information. So how do you imply from the high pass and the low pass? So if you use low pass filter, you will see an image quite blurry, right? And when you pass it through the high pass filter, you will see all the edges or the changing area of the image. Very similar to when you do the spatial domain, filtering. It's quite similar to that. So black, it's mean not pass, white, it's mean pass, okay? Because white, it's number one. One multiply everything, it remains the same value. Okay, any other question? Maybe when we go through the Python programming, you will see, you'll be able to visualize more and you might understand it better, or maybe you understand it already, because to be honest, in frequency domain, in this topic, I just want you to be able to identify low frequency and high frequency in an image and be able to read the Fourier transform of the image. When you shift the origin to the center, you'll be able to say where is the location of low frequency or the high frequency. That's all the core of this topic, the core information. So I think this one is the last topic in this chapter, in this lecture. So I was actually going to talk about not the last, but the property of the frequency filterings, and that could show the relationship of spatial filtering and frequency filtering. So I'll just start with, if you remember the third week that we have studied about the spatial filtering. What you do with the spatial filtering is when you have an image, right? You have an image f, x, y, and you have a kernel. Your kernel could be very small, and I think at that moment I use the omega or something like that, but I can use the h as well. So how you filter an image, you will just, take one smaller image, or you call it a filter, and you slide it whenever it has the overlapping pixels, you slide it through. Whenever you find the overlapping pixels, you calculate the sum of the products of the, the area that has been overlapping, and you have done that, all around. You have done that all around. So this is the filtering that we have learned in the third week. And in here, if you have noticed, I sort of have a kernel here, and I have an image, and I have filtered this image with the kernel. And the result or the output is shown here. So if you notice something, if you have like a very simple image, like, it has only a number 1 in the middle, and others will have, 0 value. So when you, I write down the kernel of my own here, 7, 8, 9 here. So I slide it through. So it all becomes 0. It's all becomes 0 until it reached the position here, right? Position here, number 9 and number 1 has been overlapped. So you find the multiplication and you get the value of 9 here. And you do the same thing all over, and you will get this as the result. So this is the filtering. But convolution is another technique that what you do, it's quite similar to filtering, quite similar to spatial filtering. But what has been different is the original kernel. We are not going to slide the kernel all over the image directly. We are not going to do that. First, we have to flip the kernel. For example, h, x, y, it looks like here. First, we have to flip the kernel first. So here is the flip kernel. And then when I got the flip kernel, I use it as the filter, as a kernel, and slide it through the image and find the sum of product for each corresponding pixels that has been overlapping between the kernel and the image. And what you have seen from the result is when you find the first overlapping is here, right? You will see that the value that has been non-zero is actually 1 multiplied by 1. So the result is equal to 1. So when I move it, so I see 2 now and 3, and then we're going to the next row. We calculate the output from the convolution. So we get the result just like here. So what you have actually noticed, you have noticed something, the convolutions and spatial filtering. So the process is very similar. What you have to do in convolution, you just have to flip the kernel first. So do you see anything? Do you notice anything, the result? If not, I'll show you this slide then. These are the process. If I cannot, explain to you more clearly, you can take a look at it later. So if you have this image and you have a kernel, right? When you do filtering, you see this as a result. You see this as a result. But when you apply convolution, what you do is you just flip the kernel. You say the result looks so much like the kernel, right? Looks so much like the kernel, right? So I will not go into the detail how they derive with the convolution, but actually, when you apply spatial filtering, you probably want to see the correlation of this kernel and the image, and it is quite similar for the convolution. It's quite similar for the convolution, but what is different is it could be derived for the property that show the relationship between frequency and spatial domain as this. So when you convert an image, an original image in spatial domain, you convert this with the transfer function in spatial domain. It will be equivalent to when you multiply the transform image, the Fourier transform of the original image, multiplied with the transfer function, or when we do the frequency filtering, we'll multiply with this Desai filter. So it's actually equivalent. So if you, so it means that you can do filtering, frequency filtering in the spatial domain, or you will convert it to the frequency and then do multiplication and then convert it back to the normal image. That's fine too, but you can also find the spatial, you can find the frequency filtering in spatial domain by using the convolution properties. Okay, so do you think do you think it makes sense for you? but when we are doing the frequency filtering, usually we get an image. We get an image and then we transform it using Fourier transform. So we get a capital FUV, right? And then what? I want to filter, I want to apply the low pass filter. So I multiply them with the low pass filter, like HUV. The HUV, if you want it an ideal low pass filter, look like this, right? This is sort of the image in frequency domain. For example, if I have a cat, it could look like, like this in frequency domain. So when I multiply them, the result, only the low pass filter will be passed. So outside outside the cutoff frequency, they all been removed. So the result from the filtering in frequency domains, it would just look like this, like this. I put the envelope around here. And this is called GUV. GUV. I think I have defined this GUV in the beginning of the slide. So these are the filter image, right? And then how do you get the original image? Just like here, how do you get the original image? You have to apply the inverse Fourier transform. So what you have to do is you have to apply inverse Fourier transform to get the GXY, which is the image after we have applied the frequency filtering. But for this property, if you convert, you convert an image with the spatial domain of the filter. When you convert the image of the spatial domain of the filter, you can get the filter image, like, once you apply the convolution. So this property trying to tell you the equivalent of how you work the frequency filtering in frequency domain or the spatial domain.
The multiplication operation, is that the filtering or the convolute?
This one is filtering in frequency. Filter. It's sort of the multiplication. It's sort of a multiplication, but convolute, it's actually this notation. I'm sorry, I haven't tell you that. This one is mean convolution. But this one is only multiplication. And both of them can be used for frequency filtering by this property.
So if we convolute in spatial domain, it's like filtering in frequency domain, right?
Yes.
How about if we convolute in the frequency domain? Is that possible?
Yeah, it's actually applied the same way. That when you convolute in frequency domain, you will also get the multiplication of the spatial domain of the original image and the transfer function as well. But we not really use this one. We mostly use the frequency, multiplication, because it is very easy. It's very easy to design the filter, this filter in frequency domain, like, the ideal low pass, the Butterworth low pass, and Gaussian, something like that. Yeah. So the importance of convolution is shown in this property. And for the spatial filtering that we have worked on it, like, on the third week, the spatial filtering here, it's actually does not apply in these properties, but you can take a look at it more. It could, it could use as the equivalent as well, but I can't remember. Maybe some of the component has to be, complex conjugate before they have do the convolution. So the amazing of convolution is it can be, convert between the spatial convolution and the multiplication in frequency, and it's all equivalent. So if I ask you to filter by this process, and this process, I hope you can do it. I just hope you can do it. I think it will be interesting for you to see the equivalent, by using this true process. And in Python, you have convol library, the convolution library, and you have like Fourier transform and inverse Fourier transform. So I hope that you can prove the equivalent of these two processes to see the same result. Yeah, but anyway, in this chapter, I just want you to see the importance of the convolutions and how they can be used to convert between frequency domain and spatial domain. So if I ask you one question to, choose to do frequency filtering by the spatial domain or the frequency domain, which one will you prefer? Will you prefer?
Convolute, easier.
Yeah, yeah, but you have to transform the big H, the capital H to H, and that's all. You can convolute and see the same result. Yeah. Okay, to make you see more clearly, we will do some. I'll show some demo. I'll show some demo. So before I show the demo, I think it's quite clear in here. So in the first part will be the ideal filtering. So I'll just summarize the program or this line of code for you. So first we get an image. So this image is sort of the f, x, and y image. And then we apply the Fourier transform here. So we actually now get the f, u, and v. And then we have shifted. We have shifted the center. We have shifted the origin to the center. And then I find the magnitude of the Fourier transform. And nothing much. I just want to visualize the magnitude. But then the part of filter, I have create a circular filter, which is act like an ideal filter, an ideal low pass filter, which will have some certain value as 1 and the rest is 0. So I have applied the cutoff frequency. Right now I use C equal to 15. So the cutoff frequency is about 15. So yeah, so this area is actually a set of code to create the H of U and V here. And after that, I multiply. This one is not convolution, it's actually multiply because if you want to convolute in Python, you have to use the convol, the convol library. But this one is actually multiply. So I multiply the image of Fourier transform and have been shipped the center as well to the ideal filter. So this one is original image, and this one is the Fourier transform of the cameraman image. I have created the low pass filter here, So I multiply this one with this one. So what happened? When I multiply this one with this one, what happened? The value at here becomes 0, right? So you look at this image. The value outside the cutoff frequency becomes 0. Only the information here is left, which is the low pass, the low frequency passing information is here. Low frequency passing. And when I have do the inward Fourier transform, so here I multiply. So I multiply, I will get the image here. And this area is just showing image. And then I shift the image from the center, the origin to the center, back to the original position. And I find the inward Fourier transform. So this one is actually a filter image. So this image is the result of the ideal low pass filter, when I apply ideal low pass filter with the cutoff frequency equal to 15, which has been configured here. And what's next? What's next is I also do the same thing, but I also change it to use, I think this one is Butterworth. So I have create set of code to create a Butterworth. You can take a look at it as detail, but basically I've just created the coordinate of the size of the image. For example, from if an image is size like 5 by 5, so I create the value in x dimension, y dimension from -2, -1, 0, 1, and 2 just here. The reason is to, imitate how the center, how the origin was at the center. And then I have just, used the formula just like I show in the slide. I use the formula that I show in the slide. So I as a row and the columns, and I applied it. So I also have the cutoff frequency and also the order that you want to design the Butterworth filter. So in this case, I use 15 cutoff frequency and order equal to 15. So if you remember, if n is large, it go down slower, but it very sharp at the zero, at the point of 0. So that's how it looks like here. And you see nothing. There's only wake or overall information of the image because it's actually a low pass filter. You can increase the size of the cutoff frequency and maybe lower the order a bit. You might get the similar result to the input image. And you can apply this with, so this one is actually the Butterworth. And I think the next section, this one is Gaussian. So I just leave some box that you can fill in. So I think I will use this exercise as your homework. So you understand the frequency components more. So I probably let you fill in some sort of the code, which is the formula of the Gaussian filter. I'm not sure when you're a first year student, you maybe, are familiar with the Gaussian filter. And this is sort of an application that you can visualize using the Gaussian filter. So you will have to apply the formula, and you can see the example of Butterworth or the ideal filter and apply this. And you will see the result of, low pass image, low frequency passing image. So you see the image is quite blurred. Quite blurred. So what is actually the usefulness of the frequency filtering? one of an example, I think you probably learn it after midterm. I think after midterm exam is you can use it for image. I think it can be used for, you can use it for image compression. But and you select whether you want to lose some information, but if your eye can still catch the information, that is fine too. But you can decrease the storage or the size of the image if you compress it by keeping only some certain of frequency bands, some of the frequency that's important for showing the whole image showing sufficient information to see the image similar to the original. So yeah, so I hope that you might seen, like, you might seen a little clearer. I'm not sure. I'm not sure if you seen a little clearer when I show the Python code like this. But yeah, and basically the core of this chapter is only just you learn about frequency domains and how do you convert it to frequency domain, and then you do some filtering using your own design filter, and then you invert it back to the spatial domain as the original image, and how it is actually look like when you remove some high frequency or low frequency. Okay, so I also give you the some exercise work that I want you to apply with the high pass filter. So it's quite similar. So just change the formula in the code a little bit. So you get the high pass filter by 1 minus the edge of the low pass filter, right? And then the result from the high pass filter, if you can remember from the previous examples, you will see all the informations of the high frequency, and that's sort of the edge, right? The edge or the changing color, the area that there are color changing in the image, or the edge, or it can be used for edge detection as well. It's quite similar to when you apply the derivatives, or you remember the Laplacian or the first derivative, you will see the small detail or the change in the image pixels, only those area. Okay, so how do you think about this? Do you think you maybe understand some of the aspect, or do you think there are anywhere that you want me to clarify, or if you want me to explain more in which area, you just let me know. And otherwise,
here, why the high pass filter give edge detection? It gives the high frequency of the picture, right?
Yes.
But how do we know that high frequency is the edge?
If you can remember the example for the, I think, first of the week. If you take a look at this this example, if you want to create a square wave like this, right? Let me remove everything now. If you want to create a square wave, right, it said that it's actually a combination of some sinusoidals, some frequency. So the red one, do you think it has high or low frequency? The red one, high or low frequency compared to the blue and the green and yellow? Do you think it has high or low frequency? Low frequency, right? So it had low frequency, and you see that only the sine wave alone cannot create the square wave. There are some information has been missing, right? And that's the small wave here, which has the higher frequency, So actually the higher frequency, it's sort of a detail in image, and it's and for the low frequency, it's actually the overall information of the image. So whenever we remove our low frequency information, when we remove everything here, we will see only the small wave, and it's very high small wave only when the color has changed. So it happens around the, the edge of the image. So that's why high frequency is sort of the small detail. It happens very, you will see it very clearly at the edge of the image. Does that make sense? I think if you tried the Python code, I just compare with how do I study this. I think it will be better to visualize what is actually going on. So I will sort of, usually I will sort of use the Python programming to see what it actually look like. Okay. So yeah, so the overall image that you have seen, they are in low frequency, and all the detail has been filled up, especially when it has the changing area. It actually has been filled up with the high frequency information. Okay, so that's actually the core of this chapter. It's actually the core of this chapter. How do you identify the low frequency and the high frequency? So do you want me to explain more in any area? Just let me know. Or if you want some time after class, that would be fine too. I'll be happy to work on it. But otherwise, I will definitely post this video after the class. Okay. So yeah, I think I have finished this lecture in frequency domain, and I will start new topic after the break, maybe. Yeah. So every time, every slide, I will sort of give you the reference that you maybe want to explore more about, for each chapter. So for each chapter, they actually have a reference, but I have never mentioned that. But if you want to read more about the information, there are reference for each slide that you can take a look. I think it's in the last slide. Okay, so before we come back, I think we might have some break, like 10 minutes, okay, before we start the new topic. So I think I'll ask you to come back maybe at 1442, yeah, 1442 back. Okay. Hello. Hello. Can you hear me? I always trying to check my my microphone just in case it's not get in to the Zoom. Hello. If you hear me or if anyone has back, can you type a smiley face if you not feel so, even if you're not feeling so. Oh, thank you. If you are here already, can you type a smiley face? Thank you, thank you. Oh, so how so I have show the proposed midterm exam here. So everyone is okay with this date, right? I have posted in Discord, but it seems like no one will have another exam on this day. So I think it will be this day. But for the protocol or how we going to have the exam, I'll let you know maybe next week. So are you still okay? Yeah. So so if you have any question or anything, just let me know. Or if you understand, it's fine. It's okay too. So I think the next homework, I think I plan to let it out after the Weeblet chapter. Which would be next week will be Weeblet. Okay, next week will be Weeblet. So will probably be next couple weeks. Next week. But if I cannot finish the Weeblet next week, it might be the following week, which will be a week before your midterm exam. But yeah, I think the midterm exam will be an exam from the first chapter, from the first lecture to the Weeblet, topic. But I haven't really talked about it just yet. But yeah, the next topic after image restoration this week will be Weeblet. So hi everyone. So what about the others? Are you back? If you're back, just put a smiley face for me. So how do you feel about the how do you feel about using Zoom? Because there are some other lecture that I use YouTube as well. Do you want to request for YouTube, or you're okay with the Zoom, the class in Zoom? You can give me some opinion. Do you want YouTube as well? So I can try to, put the stream through YouTube, because you can stream to YouTube while we use Zoom as well. But I'm not sure if it's a preference for you, or in here it's okay enough. Just let me know about your opinion. And I hope the microphone is okay, yeah? It's clear enough, yeah? Okay. Ah, okay. So good. Okay. Okay. So if that is okay, I'll keep I'll think about it anyway. Yeah, but yeah, we'll definitely use Zoom, but maybe someone would like to take a look at YouTube, because they can, you know, backward or forward the video at the same time. And if you don't understand anything, you just, you know, go backward a little bit and then you fast forward maybe, you know, 2 times to catch up the class in real time. Some people do that as well. So if you prefer that, I'll open it for you. I'll open it for you, but it's mainly by Zoom because I would actually want to hear your voice. It would be nice to hear your voice as well, even though not so much or anything. Yeah, but yeah. Okay. So very good. Okay, so we're going to the new topic today. Yeah, a new topic today. Okay. And let me ask another opinion. Do you like the lecture? Can you give me the portion of lecture and exercise? I mean like Python exercise. Can you give a portion like, oh, I think this class should be 100% lecture. Or if you want like 70% lecture and maybe 30% Python. Can you give me some opinion? Like, do you prefer like 100% lecture, or maybe sometime for Python, or maybe 50% of Python, or do you have like, you know, any opinion about the portion of the lecture? You can give me your opinion like very freely. Today is very quiet. I really want to talk to you. Oh, one of your friends says 70, 30. Prefer easy exam. Okay. Prefer easy exam. Okay. 30% Python is okay. Okay. 0% quiz. We don't have quiz just yet. But at the end of the class is in-class exercise, right? It's not actually a quiz, but I don't know if we really mean like real quiz, right? We don't have yet, but yeah, we don't have this yet. A lot of lecture, I will forgot it anyway. Okay, written and okay, 70-30. Okay, thank you for your opinion. So I think I was trying to balance. I think it would be nice to take a look at some code, even though I actually put it in the lecture. So hopefully you can, you know, try it on at your home very easily. But it would be nice to do it, you know, in the class as well. Okay, 60% lecture, 40% Python. Okay, okay. So 1/3, probably about 1 hour. Okay. 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 So now we are in the new topic now. Yeah. So this chapter, it's about image restoration. So what is actually restoration for you? Restoration. When I first talk about restoration, what do you think about it? Restoration. Restoration. Do you think it's similar to enhancement? Enhancement. Do you remember we have studied about the enhancement, and I asked you to, you know, create a filter of your own. I haven't taken a look at your homework just yet, but yeah. So what do you think when I talk about the image restoration? Restoration. What has come first in your mind? One word. One word in your mind. Restoration. Restore. Old movie. Fixing. 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 Very good word to describe how we, you know, fix an image. Very good word. Yeah, I'm helping you fixing the image. Recover detail. Recover some detail. All right. Yeah. Old movie. Like they have some noise, right? So in this chapter, I have taken a look at the textbook, and I think I have provided a textbook at the reference, you know, last slide here. just here. But I have found that, oh, there's quite a number of mathematics involved. So I have modified it a little bit. Just want you to see the fundamental image restoration, even though they'll not really use it, you know, in practical way. But it's not like it's not practical, but it's actually the fundamentals. So right now, you know, it's the era of the deep learning and machine learning. So sometimes when you work with image processing, it might not be the first choice for any problem, but it's actually a fundamental. And I hope that I think it could be useful in one way or another when you're working or handle with image or you're working with image processing. But yeah, there are some basic idea in image restoration that I have organized it for you. So for the objective of this chapter, I think I would probably finish like, you know, first half, and another half I will move it to next week then. So for this chapter, I actually want you to know about many different types of image degradation. Degradation is sort of, you know, the grade has been, you know, decreased. The grade of the image has been decreased by some reasons, So we'll see what is actually, what could be the reason for that, and how do you know, implied it in image processing. And then there are some techniques, very basic techniques that you can use it for, you know, to apply it for different degradation. So yeah, so the content is only about degradation and restoration. So in this chapter, we are going to talk about how do we remove, or like your friend said, that how do we fix, right? How do we fix an image when there are some problems? And what are the cause of the problems? The cause of the problems can be caused by the acquisition of the image. The acquisition of the image, that how you acquire or how do you capture an image. For example, some type of the image could, you know, contain some noise. For example, the satellite image, maybe they don't really have like so much details in the image, or maybe there's detail, but it could be, you know, affected by the weather condition. The weather condition could affect the image of the satellite image. That's the one of the examples. And there's some other noise involved as well. So in here, the word degradation, it will imply that it could be noise, it could be some noise, some certain noise, or there are some optical effects. For example, it's out of focus, like whenever you take a photo for your friends and it's blur, so your friend will ask you to capture another one, right? So that could be a problem as well. So that could be another problem, blurring image due to the camera motion. Sometimes, you know, when you take a photo of moving things, they have like, you know, certain motion. So it could affect the quality of the image. So how you fix it? So in this chapter, we will talk about two components. First, we will fix it with the neighborhood operation. This one is similar to the spatial filtering. Spatial domain, spatial filtering, quite similar too. And another one is we are going to work with the frequency domain again. And how do we, you know, recover or restore an image using the frequency domain? How do you restore an image using this operation? So that is all about this chapter. So first of all, I would like to talk about the definition of image restoration. Yeah, like your friend said, it's trying to fix or recover or reconstruct an image that has been degraded by some knowledge that or some degradation phenomena. And the model of image degradation has been, it it is modeled in this way. First, you have an original image. For example, you have a very clear image. The degrade image, it has been degraded by some certain function h, and you probably can, guess that the h will be working in the frequency domain later on. Yeah, but yeah, the image has been degraded by a certain function h, the certain function h, and this this process of degradation is the process that is being defined by the convolution. And in the textbook by Gonzalez that I have detail in the reference, they have the proof that how do you identify the degraded image in terms of the convolution, and I don't want to talk about it in the detail, but this is how you model the degradation. So first, it has been degraded with some function, and it has been identified by the convolution process. And then what? And then we have some noise as well. So noise is not affected by the convolution process. It's actually the affected by the addition, only addition, the addition process. So an image can be, degraded by some function by the convolution, or there are some noise has been added in an image. So this is how I explain the process. That first you have a very clear original image. If you can find the image has been degraded by the function h, and then has been added with the noise in spatial domain, still in the spatial domain, you get the degraded image gxy. So this one is actually degraded image. So when you pass the restoration process, hopefully you will get the image that is actually similar to the original image. This one you can call it like a reconstruct image. I might call it reconstruct image, or estimated image, because we're not sure it's actually the same image, but yeah, it's actually estimated image. So these are the process. When the image has been degraded or added by noise, we can work on the restoration, and then we get an estimated image, which should be similar to original image. So that is image restoration. And as we talk about the property of the convolution in spatial domain, in frequency domain, you see that there are actually the multiplication between, the degradation function in frequency domain and the image in frequency domain, and added by noise in frequency domain as well. But about 70% of this lecture will not talk about the frequency domain. We'll talk about the spatial domain. So what are the type of degradation? What are the type of degradation in your own mind? Can you give me some example of the degradation that you maybe found in an image? Can you give me some example of the degradation that could affect an image? I just want to take a look whether there are like any other degradation that I have not think about. One of your friends said low resolution. Oh, your friend asked about H and F. I'll talk about it very soon. But yeah, can right now you give some example of image degradation? One of your friends said low resolution. Low resolution. So when you scaled it or large it, you find it unclear, right? Sasarin said blur age, and Grit said blurry image. Anything else? Anything else? Anything else? In this case, your friend said wine get. I'm sorry, I don't know how to pronounce this one. What is actually? Can you explain about it? Can you explain about this word? Satra, can you explain a little bit more? I want to know. Anything else? Anything else? So if you think about image degradation, the quality is low. The quality is low by what's the problem? One of your friends said the corrupted pixel. Corrupted pixels. Maybe that pixel is not really represent the actual value, right? One of your friends said noise. Oh, okay. One of your friends said noise. Yeah, could be noise as well. And Satra explained that word. That word is like the edge of the picture is black. Oh, you mean like the filter when you apply the filter, like the vintage image or something like that? And maybe I should Google what it actually look like. Because I think I'll type it correctly. Oh, okay. So it's actually just like your friend said, that the image is sort of, have the black color over here, and in here it's original image, right? Okay. Your friend said there's some noise or something like that. Okay, like an old vintage picture. Yeah. So that could be one of the degradation that I haven't really thought about it. Yeah, that's correct. So let's take a look at some more example. Yeah, some of the example your friends has mentioned. Oh, let me identify the F and the H of written and ask about what is actually H and F. So sorry, H is actually the transfer function. No. I should say that it's actually a degradation function, which is quite unknown. It's often unknown. Degradation function, and it's actually in frequency domain. How do you know it's in frequency domain? Because it's capital H, right? The capital H and the U and a V. So it's actually the degradation function that there are some certain problems that create an image that it's sort of degraded. And the F is actually the image, the original image, which has been transformed by the Fourier transform. Yeah, so it's capital F and the U and V. Okay. Okay, anything else? Your friend said that when there is too much light exposure, yeah, that could be degradation as well. When the image is very bright, right? Very bright, right? So I was thinking that maybe in the light exposure could be maybe fixed with the image enhancement. Maybe if you apply some sort of transformation to bring down all the higher value, but then maybe the information is lost already, so maybe the image cannot be restore or recover, but yeah, it depends on the case anyway. So the example that I've shown here that your friends talk about as well, for example, low resolution. Yeah, low resolution. So the kitty looks very blocky. Very blocky. So because of the resolution is not enough, and it doesn't have enough information. Some people said it's quantized noise. Yeah, quantized noise. But if you recall the beginning of the class that I've talked about the quantized and sampling, right? Yeah, that could be affected by the sampling and quantization. Moreover, you have optical blur. Yeah, so the image is blur. so you not see very clearly about the image. Anything else? There are motion blur as well. Yeah. Do you think this image is motion blur or not? The motion blur can be caused by when you move the camera, right? Or even the person is sort of moving very fast. But in this case, I think the kitty stands still, but the camera is moving. No, I just used the filter. Okay, so here there could be a motion blur as well. And there are also some noise, like your friend said, there are some noise as well. Like we have Gaussian noise. We will talk about it, what it actually look like. There are some Gaussian noise, and there are another name that S&P noise is not the restaurant, right? S&P is actually salt and the pepper. I'll talk about it later on about noise section. And there are also periodic noise. Oh my God, the kitty has been affected by the sinusoidal wave all over. You probably know how you can fix this image, right? At the end of this class, you will be able to fix the kitty in the sinusoidal wave. Okay. Yeah, so there are many different type of degradation. Degradation. So the noise, let me classify a little, like really quickly. The noise can be S&P noise, salt and pepper, or the Gaussian noise and the periodic noise. But when we talk about the quantization noise, not sure it's actually the noise, but it could be the function of degradation. But optical blur and the motion blur, it's definitely degraded by a degradation function. So yeah, there are some types of degradation in an image. And how are we going to fix all of this in this class? No, no, there are some problems that we are unable to fix it, and some problems that it depends on the amount of the noise as well. If there are quite a lot, it could be very difficult to recover. Okay, so let's start with first part. In the first part, just forget about if you remember the models of the degraded image. If you remember, there are components of the degradation that has been convoluted with the original image. So just forget about the degraded function. In the first part, I will talk about noise only. Noise only. So the image is degraded by or is affected by only noise component. So noise look like this: eta of x and y, the function eta of x and y. So the GX actually a noisy image because it is formed by the original image, right? It's actually the original image. What I've been writing. The original image and has been added by the noise, by this type of noise. So what is the case of the noise like this? It could really happen sometimes, especially in the past. But nowadays, the technologies and the cameras are quite good quality. Even though it's a cheap price, you still get like a good quality camera. But there are still some types of image that there still be caused by some noise as well. For example, when you send one image to, transmit one image to another place, or if you get an image from the satellite camera on wireless transmission, and it could be affected by the network cable or something like that. So we might need some process to create an image. So actually, the type of the noise are various. There are a number of type of noise, but in here, I think I'll talk quite a lot about the salt and pepper noise, a very simple one, and Gaussian and the periodic noise, because we have learned about the frequency domain. So it might be useful to learn how you remove noise, especially the periodic noise. So what is actually salt and pepper? The first one, salt and pepper, it could be called as the impulse noise as well. The impulse noise. The impulse noise or the binary noise. The binary noise. It resembles salt and pepper. What is the color of salt? What is actually the color of the salt? Do you eat salt? Oh, it's not good for your liver. So yeah, the color of the salt is white, right? And the pepper, it's sort of blacky or gray, but yeah, you can talk about this type of noise is sort of a black and the white noise, the black and the white noise. So the distribution here is sort of the probability of the intensity of the noise in an image, the probability of the noise in the image. This one is actually the intensity. So this is sort of a binary image, right? The binary noise. So they sort of have like two different color. So it could be low value, low intensity. It's sort of maybe a black color, and the white color. It could have like similar probability or maybe not, or it could be, different. So the distribution of the salt and pepper does look like this. And they have some probability for a black color and the white color, and it will be 0 in other intensity. So they were saying in the process of when we digitize an image from analog to digital, there could be possible that maybe some value has been, corrupt. Some image value has been corrupt. So it has been represented by the black value or the white value. So that's how the salt and pepper noise has been created. So what do you think about the A and B could be for the 8-bit image or the grayscale level? So what do you think A and B could be? What's actually A and B? So actually A and B, it's sort of here. I already write the quality in terms of color already. So the black would be 0, right? And white would probably be 255. So I answer it myself. Okay. So yeah, it should be like that. So yeah, A and B could be 0 or 255. Okay, so that one types of noise. And in Python, when you want to play with the image restoration, there are many different types of noise in the scikit image library. You will have to start by import the scikit image util, and there are a function called a random noise. This random noise, you can add an image and you can select the mode of the image that if you want what types of the noise. For example, S and the P, which is mean that salt and pepper, right? So on the right hand side, I have provided you the documentation that you can link to the library, and you will see that at the mode parameter, you can select many different types of noise as you wish. Yeah, so you can be able to create an image has been affected by noise, and maybe you can use it. So yeah, and there are also some other parameter which is called amount. The amount is actually the proportion of image pixel that to be replaced by the noise value from 0 to 1. So I think the default is about 5% of the image, But if you want to change the density, I think it's the density of noise. The density of the noise you can change at the amount parameter. So let's take a look at, I think there are some image of the image that has been affected by the salt and pepper noise. So this one is original image, the twins image. And this one has been affected by salt and pepper noise. And I think the density, it's sort of a default value is equal to 0.5. So it's about 5%. So it's very large, right? Yeah, it's very large type of noise. So there's a mix between black and white color in an image. So when you increase the density, so the image has been, a lot affected by salt and pepper noise. So yeah, that's the first type of noise that I have show you today. The second one is the Gaussian noise. The Gaussian is everywhere in signal processing, in image processing. So Gaussian is sort of a distribution that show that it's very high probability here at the mean value, right? So the noise could be generated from the Gaussian distribution by these equations, and you see that most of the noise or the intensity of the noise will often be grouped because the probabilities of the value that near mean value is quite high, right? So there are some certain value that has been classified as a noise when you use Gaussian noise. So there basically it just has many different color intensity, but it's also depend on the probability that could occur in an image as well. So the Gaussian noise is not only mixed by one or two color, but it's actually mixture of intensity. And the same way you can use random noise, and you can use the mode as the Gaussian because Gaussian is sort of a Gaussian noise. And you can configure the shape of your Gaussian distribution by the variance and the mean value. So let's see the example. So I have created an image has been affected by Gaussian noise. The first one, I have not configured anything, but the second one, I have add the variance and the mean value. So the mean value is actually just here, right? And the variance is just how wide is your image. How wide it's your distribution. It's mean that it could have more probability to have some other color, right? Other than the mean value. So let's see. So when I change the mean from 0, it actually has to be normalized, okay? It has to be normalized to 0 mean. So I can configure any type of mean around 0, but the default, they are normalized to mean 0. So if I configure the noise at the mean value at 0.5, so it means the color, the intensity is a little bit higher when you shift the mean, the brightness of the image is higher. So when I apply this type of noise on the image, you sort of see the image has been include the Gaussian noise and the image show a brighter color. Oh, it's quite too bright, right? But yeah, it actually has the Gaussian noise inside. But for the original mean value and the variance, you will see that there's some noise in an image, and it has different intensity. It's not only black and white, but very many different intensity compared to the original image just here. So yeah, the mean and the variance could affect the noise on the image. So this one could imitate some sort of the light exposure on the image in the camera, okay? And this one, I configure the mean as a minus value. As I said, the intensity has been normalized, so it could be, any value around 0 by the Gaussian distribution. So yeah, the image has been corrupted by Gaussian noise. And you have seen that when we talk about noise, we talk about the probabilities. So there are actually many functions that could be identified for noise. I have taken a look at textbook that I have give you a reference by Gonzalez, but I really can't I really can't identify that what type of noise could be present in anywhere. But yeah, they could, you know, estimate the noise function by different probability density function. It could be Gaussian or it could be Rayleigh, and you see this one, the mean value is sort of, you know, dark a little, or it could be a uniform, so it means it could be noise could be any color from A to B with the same probabilities, or it could be a pepper and salt. I think this one is pepper and salt, but different probabilities. Or it could be exponential. Yeah. There are some example in textbooks, so you can, you know, you can generate noise using different distribution. And there, the third one is the speckle noise. The speckle noise is sort of different from the previous noise because the previous noise is sort of an image has been added by the random noise value on the image. But for this one, instead of adding, it's actually multiplicative noise. It means that you have the noise, you know, distributed over an image, and it has been multiplied on the original image to get the you know, degraded or the distorted image I of the I and a J. Why they have used I and a J, but yeah. And it happens a lot in many different applications like radar or you know, ultrasounds, and even the medical image like the tomography image and the microarray as well. So the example of the speckle noise that you will see, for example, this image on the left is show the speckle noise on the ultrasound image, and they were trying to use the statistical method to remove the speckle noise, but it's actually very difficult for me to you know, to identify. But if you see the combination of the color that it's actually, you know, look very much different, look very much strange in the combination of, you know, red and green and blue, and you see a very different color. So I think that is sort of the effect by the speckle noise. They're trying to use the many different techniques like a statistical technique to estimate or to recover an ultrasound image, you know, to be without the speckle noise. And this one is show that if the levels of the noise is high, it will be multiplied and you get a very high noise. So it's multiplicative noise, type of noise. So your friends ask, is it multiplication or convolution? I'm sorry, it's actually multiplication. So yeah, it's actually, yeah, it's multiply. Yeah, just multiply, like, you know, corresponding pixel. Yeah. Yeah, maybe I should, like, you know, take a look at this one more. Maybe I should remove it so you will see it easily, just multiplication.
The previous two noise is addition noise.
Yeah.
So the salt and pepper and the Gaussian is addition noise, right?
Yeah, it's add to the original image. Yeah.
Okay. Can speckle noise be addition, because it's a model can be random by added to an image?
You mean like model by the random value
like
add
speckle
to
noise,
the image?
Can it be addition too? I just curious about the
Yeah, I
Okay.
wasn't really sure. Yeah, but it's actually said add. But how do you add? But add by multiplication value. I'm sorry, but the definition is actually multiplicate. So I think they are not talking about the addition here. So the basic models actually just simple multiplication. But if there were an addition, maybe I don't know. Yeah. 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 Okay. So it's just how you describe that when the noise getting high, like very high value, and it could be called the speckle noise. But we're not going to recover an image in speckle noise because it's very difficult. I think in here we are going to recover using image that has been corrupted by periodic noise, salt and pepper, and Gaussian. Only like the basic one. Yeah. I think this one is electromagnetic. Sorry, I think I've seen it sometimes and I haven't removed it just yet. So the last one is periodic noise. The periodic noise, as you can see, that the image has been, corrupted by some sort of periodic types of noise. Have you ever seen image has been corrupt like this? Have you? Have you? Have you ever seen an image has been corrupted by the periodic noise or not? Not really see that much, right? But there are some flickering when you capture an image that have different sampling rate. But yeah, it's not so much. But it's actually when we talk about the periodic, sometimes we not sometimes, but most of the time we think about the electrical interruption or electrical interference, because, for example, our system is sort of 50 hertz, right? Our electricity system. So we could probably be, an image could be interrupted by some sort of electrical, components that have some frequency that has used in the electronics device. Or it could be some sort of electromagnetic interference as well during the acquisition. Maybe it could be, affected by some other EM source, like, some other type of the wave, not only just electrical interference. So in this case, definitely we will reduce it using the frequency domain filtering. Yeah, we're going to do this one as well. Yeah. So for this chapter, I think we have some times, and we have the in-class exercise, and we have the periodic noise. So actually, I have one exercise here that I already uploaded the NASA the NASA image on my course field, and in the area here. The NASA image is actually look like this, right? The original image. It seems to be okay, I think. But then I have, right, a small set of code to add the periodic noise into the image. I have add set of code like a periodic noise add into an image, and then you see this the image that has been affected by the periodic noise, which is just the original image, but the type has been changed to float, so it will be able to combine with the floating numbers. And I've added with the periodic noise that I have created using the sinusoidal, the sine function. So yeah, so this is actually the image that has been interrupted by periodic noise. So what I want you to do before we finish today's lecture, so I want you to read, I want you to open the Colab and read this image that I have uploaded for you. And then you copy the whole set of the code here. I think you can copy it, right? You copy it here, copy everything. And then I want you to apply Fourier transform to see what is actually this image look like in frequency domain. So this one, I think we're going to do it together. Yeah, about maybe 10 minutes before we continue to the exercise on my course room. Yeah, so I give you like 5 minutes to get started with the Colab, and I will open it and work with you through, because next week you will have to use some certain techniques to remove the noise from the image. Okay, so yeah, just want you to try this exercise, just copying the set of the code that I give it to you here. And can you add some set of code to see the Fourier transform of this image? And I will do it with you together. Okay? Okay, so let's do it together. So once you do it, I will ask each of you, not each of you, just all of you, that what is the Fourier transform of this image would look like. Can you guess now? Can you guess now what is actually what it will look like in frequency spectrum? Can you guess the FT of this image? If you can guess, just let's code it together. Okay, I will open the Colab. I think I sort of having okay, Colab. Okay, so I create like a new one. So let's do it together. Okay. So today is sort of lecture 05 and it's restoration in class. Okay. So I would need the NASA image, right? The NASA image. So I will just add the NASA image. Image processing. Okay, I have uploaded the NASA image here now. So next, I will get some code that read an image and create the noise and add it into the image. I'll go get it from the PowerPoint. But then I would probably need the CV2, right? And also NumPy as well. Okay. Anything else? I think that's all. Okay, go get the set of code from the lecture. very quick coding. Okay, so you probably not see anything because I haven't show up anything. So I will import some other library like Matplotlib so I can visualize the image. So this is actually the original image. I have make it show so I can show another image. So the image has been interrupted by the periodic noise is image PN, right? Okay, let's see what it actually look like. Okay, I'll change it to the familiar shade of grayscale. Yeah, so you probably seen the image has been interrupted by the periodic noise. And then I'll let you apply the Fourier transform. So I'll give you 1 or 2 minutes. On this image. For Fourier transform, I use the one that belongs to NumPy, so I don't have to import anything additionally. So I think that's fine. Okay, so what's next? You will just have to copy the result for a quick process. So to find this image in periodic in frequency domain, I have convert an image into the frequency domain F. It actually should be like big, a capital F, right? But yeah, doesn't matter. And then what's next after Fourier transform? What's next? What's next? Can you remember? Can I show it now? Your friend said shift. Yes, I will shift it. So I'll shift it using FF shift with a big F. So a VF shift. And what's next? If I want to take a look at it, you cannot look at the detail of the complex number, right? You have to find the spectrum. Your friend said lock. you can copy me all your code so I can copy. So your friends can copy into their work. Okay. Very good. Very good. Oh, okay. Oh, just exactly the same. Very good. Do I have like set of code in the back or something? Because you seem to do it very great. Okay, so I'm trying to make the same parameter names. All right, now I can take a look at. Okay. Very beautiful, right? It's not nice, right? So you think what is actually the wing like a star in the image? Actually, if I take a look at the original image like IMG, right? It will be different. And how it's actually different. Yeah, so this is actually the Fourier transform of the original image. And this one is an image has been affected by noise. So you see the difference, right? Yeah. So that's why we will be able to remove the noise in the next lecture. In the next lecture. Yeah. You can do a filtering from the previous lecture as well, or there's something that I will show you next week then. Or do you want to study more? More 3 hours? I'm kidding. Okay, so yeah, so we'll be able to remove some noise here, or you can try it at home before next week. All right, you've seen this, star on the left corner and the right bottom corner here. So it's actually noise. Yeah, it's actually the noise compared with the original image, the Fourier transform of the original image. Okay, so yeah, next week we will continue from this collab because we are going to remove the noise. All right. Okay, we have 15 more minutes, so I would like to take these minutes for you to do a little exercise to recap, or to summarize what we have studied in this lecture. It's definitely about the frequency domain and also about the noise as well. So I will turn on I will publish the oh, it's raining. I will publish my course view in class exercise. Okay, so I'll let you do it like 10 minutes, and I'll use 5 minutes to summarize to provide a solution. Okay, so it's in class exercise number 5, and I'm going to publish it in class exercise number 5. Okay. I think right now it's actually published. Can you take a look whether it's published? Yeah. So just there are only about 1, 2, 3, 4 questions. So maybe like 5 minutes. Yeah, 5 minutes. I've given you 5 minutes. So 15, 5, 1, 15, 5, 1. And I've come back. Okay. 5 minutes for the My Course View exercise.
Can I ask question?
There's about 55 response. 59. Sorry, 10 more. ค่ะ
Can I ask you about the log, the magnitude spectrum?
Yeah, sure.
So, what are the different of the Fourier spectrum? Like the magnitude spectrum, what does it do? Like I know in Python it just changed the picture to the like the spectrum, but why is it log?
We use log because you can remove the log and you will see that the image is very dark. So the image is very dark. It means that you will not see so much of the detail because all the information, most of the information in an image is actually at the center or the low frequency. So we apply log to make the low value getting a bit higher. If you remember log transformation in second or third week, yeah. So log transformation will bring up the small value for us to see. So that's why we have apply log. It's a very good question. So I'll show you in the Python in Colab then, because we have showed it already. Where is it? Okay. So I haven't shared it just yet, right? Okay. Okay, so now you've seen, I haven't opened my video just yet. Okay, so now you've seen the image here, right? So if I remove the log transform here, maybe I'll try with the new one. Yeah, the new one. And you'll see that we have add one as well because log cannot be zero. Log cannot be zero. So we add one because we don't want them to be error. So if I remove log here, when we calculate the absolute, it's already the value of the complex number already, right? So let's see what it actually look like. Yeah. So this one is the Fourier transform, the original Fourier transform of the image. It's very dark, right? So you won't see much of the information because it's actually, very large at the center. So that's why we apply log transform to, bring up the small value to get the detail clearer. That's only the reason. Okay.
Okay, so so here the white part that's represent the strength of the frequency, right?
Yeah.
So
here,
in the yeah, so that's mean in the top picture, that's the white part is the because the strength, even though it's the low frequency or high frequency, the strength is a positive number, and it would be like white anyway, right? คือตรงสีขาวเนี่ยมันไม่ได้บอกว่ามันเป็น low หรือ high ถูกป่ะครับมันแค่บอกว่า strength มันเยอะหรือเปล่า
ใช่ strength เยอะมากถ้าค่าขาวก็คือสูงมากแล้วก็ตรงนี้มันเป็น low frequency ด้วยเนี่ย low frequency high frequency ก็น้อยลงอะไรอย่างเงี้ยค่ะ
แต่ว่า high frequency นะครับมันไม่ได้บอกว่าถ้า high frequency จะสีขาวหรือ high frequency จะสีดำถูกป่ะครับ
มันมีค่าอยู่นะในแต่ละจุดอ่ะ
มันเป็นค่า strength ไหมครับที่อาจารย์บอก
ใช่ก็ถ้าเกิดว่า higher frequency ไปทางนี้ใช่ไหมมันก็จะมีค่าของมันอาจารย์เข้าใจคำถามถูกไหมเนี่ย
เปล่าครับคือแค่สงสัยว่า strength นะครับ strength มันบอกสีถูกไหมครับว่ามันจะดำหรือขาว
ใช่
แต่ว่าทีเนี้ยposition ของ index อ่ะมันถึงจะบอกว่า low หรือ high frequency เพราะฉะนั้น strength ถึงแม้ว่าตรงเนี้ยมันจะสีขาวตรงเนี้ยมันจะสีดำหรือสีขาวเนี่ยก็ตามมันไม่ได้บอกว่าอันนั้น low หรือ high ถูกไหมครับ
low frequency หรือว่า low strength นะ
low frequency ครับคือ
เนี่ย low frequency เนี่ย low frequency เพราะตรงนี้ DC แล้วก็ low frequency แล้วก็เริ่ม high ขึ้นนี่ค่ะ
แต่ถ้าพูดถึง strength ก็คืออย่างเพราะว่าตัวสีอ่ะมันบอก strength ถูกไหมครับ
ใช่
เพราะว่าเป็น intensity
ใช่มันก็จะบอกว่าอันเนี้ย strength สูงมากๆเลยสำหรับ low frequency high frequency อ่ะมีนิดเดียวเนี่ยเพราะว่ามันเป็นสีเข้มๆแล้วไงตรง high frequency
ก็แปลว่าเรามี low frequency เยอะในรูปนี้ครับ
correct ถูกต้องเลยค่ะSo your friend has asked about the strength in the white color. So I want to explain that there are the strength of the low frequency, higher strength than the strength of the higher frequency, because higher frequency is outside, right? And the lower frequency is here, and it's white, just mean the strength is high for the lower frequency. Okay, so let's take a look at my course view before we finish the class. Okay, so it's actually here. Okay, so the first question was actually the multiplicative noise. So this one is speckle noise. Let me change it to your friend question, your friend answer, sorry. So I have to look at the graph here. Okay, so yeah, most of your friends said it correctly. The multiplicative noise is and speckle noise because other they have been add to the original image, but only speckle noise has been multiplied on the image. So the answer is A. So the second one, the convolution and filtering are the processing of two images in frequency or spatial domain. This one is correct. You can do convolution or filtering in any domains. And convolution of the two images in spatial domain is equivalent to the multiplication of the Fourier transform of the two images in frequency domain. This one is correct. Correct, still correct. The third one is multiplication, the other way around from the B, which the multiplication of the image in spatial domain is equivalent to the convolution of the Fourier transform of the two images in frequency domain. This one is still correct as well. You can take a look at the slide that, in the frequency filtering that I've shown the B and the C in the equation. And the dog, convolution and filtering are exactly the same process. So this one is incorrect. So most of your friends answer it correctly, okay? The third one, what is the result from high pass filter? This one is actually the C, the number C, because high pass filter will passing all the high frequency of the components of the image. So they are sort of the changing location, small changes. You think about, 1 pixel change immediately. So it's sort of small detail. So it's the edge image. So that's the edge image. The last one, what would be the image result from the cutoff frequency of low pass filter? The smaller cutoff frequency of low pass filters mean the smaller information will be passed. So the smaller cutoff frequency show that the information come out very little. So you will see a very wakey image, like a very unclear image. But when you cut off information more and more, you will see a clearer image, just like number C. So it will be ordered in terms of B, A, and C. So most of your friends answer it correctly. So very good. So clap to yourself. Okay. So I think today it's all now. So I think I'll finish the class here. So if you have question, just drop the question. You can open the microphone as well, or you can ask in Thai or in English. Okay. So yeah, I think that's all for today ค่ะ มีคำถามไหมคะเด็กๆอยากถามอะไรไหมค่ะถามเลยค่ะ
เราจะคำนวณตัวconvolution ของใน frequency domain ยังไงครับถ้าเทียบกับ spatial คือ flip
มันสไลด์ใช่ไหม
kernel ครับ
เหมือนกันเลยก็คือมันก็จะเป็นหน้าตาพิกเซลใน frequency ใช่ปะก็เอามาสไลด์เหมือนกันถ้ายิ่งใหญ่มันก็แบบมันก็ต้องสไลด์เยอะนิดนึงอย่างเงี้ยค่ะ
แล้วมันต้อง flip ไหม
ต้องอะไรนะ
หมายถึงว่ามันต้อง flip ไหมครับ
flip ไหมflip ด้วยflip ด้วยใช่ต้อง flip ด้วยขอโทษทีเอาตัวไหน flip ก็ได้ค่ะจะ flip F หรือ F หรือ flip H ก็ได้แต่ flip ตัวเดียวได้ผลเหมือนกันค่ะโอเคค่ะคนอื่นมีคำถามไหมคะถ้าไม่มีแล้วเพื่อนๆสามารถออกได้เลยนะถ้าใครมีคำถามถามได้นะคะ Your friend can leave the class but if anyone else has a question you can ask me okay so no question today not much of question today
ครับสงสัยตรงสเปกตรัมใน magnitude spectrum อะครับคือแบบยังไม่ค่อยเข้าใจว่าแบบตรงสเปกตรัมมันหมายความว่าอะไรสมมุติว่าแบบอย่างครั้งที่แล้วอย่างเงี้ยที่มันเป็น cross ไป cross มาอย่างเงี้ยครับคือ
เป็น x ใช่ไหมมันก็คือเหมือนค่าสีของแต่ละพิกเซลอะใน frequency domain UV อะค่าสีของมันที่เป็นสีขาวก็แปลว่ามีค่าสูงถ้าเป็นสีดำก็มีค่าต่ำหรืออาจจะเป็นลบด้วยนะ
อย่างนั้นก็คือถ้าสีขาวอย่างเงี้ยก็แปลว่า frequency ที่ index ตรงนั้นนะครับสมมุติว่ามันอยู่ตรงแบบตรง ซ้ายบนอย่างเงี้ยก็คือแปลว่า high frequency ตรงนั้
ใช่
นมันมี
ถูก
ค่า
ต้อง
สูง
ใช่ ถูกต้อง
แล้ว
ค่ะ
มีค่าสูงมันแปลว่าอะไรครับ high frequency ก็คือมีจำนวนพิกเซลที่เป็น high frequency เยอะเหรอครับ
ใช่ มี amplitude ที่คูณเข้าไปอ่ะเยอะมีแบบมีมีค่าเหมือนกับ amplitude เยอะอ่ะว่างั้นเถอะ
amplitude เยอะแล้วเกี่ยวอะไร amplitude ตรงนั้นเย
นึ
อะ
กนึกถึงสัญญาณคอสไซน์เนาะถ้าเกิดว่า amplitude เยอะมันก็จะสูงอย่างเงี้ยแต่ถ้า amplitude น้อยก็คือจะเตี้ยก็แปลว่าแบบเปลี่ยนแปลงนิดเดียวอย่างเงี้ยเข้าใจปะ amplitude สูงก็แปลว่ามีการเปลี่ยนแปลงในรูปแบบความถี่นั้นอะเยอะอย่างเงี้ยค่ะ
แล้วถ้าเทียบกับรูปออริจินอลอะครับแปลว่ารูปออริจินอลมี high frequency ที่สูง
ใช่ใช่
ก็คือ
มีการเปลี่ยนแปลงที่ความถี่นั้น
ปริ
สูง
มาณ high frequency เยอะแล้วครับ
ที่มันจะมีที่ตำแหน่ง UV อยู่ใช่ป่ะก็แปลว่าที่รูปออริจินอลอ่ะมันมีการเปลี่ยนแปลงในความถี่นั้นอ่ะเยอะมากในภาพจนต้องขึ้นมาเป็นแอมพลิจูดที่สูงมากเลยจริงๆแล้วดูจากรูปเมื่อกี้ก็ได้ที่มันเป็นสัญญาณไซน์ที่มันเอียงๆอ่ะมันเป็นเพราะว่ามันมีแอมพลิจูดสูงมากที่จะเจอแบบสัญญาณไซน์ที่ตำแหน่งเชฟรูปแบบนั้นนะคะมันก็เลยแบบขึ้นมาเป็นสีขาวเลยเนี่ย
อาจารย์โชว์รูปให้ดูหน่อยครับ
ได้ถูกไหมเอาถูกเดี๋ยวแป๊บนะคะขอเปิดสไลด์เปิดตัวมันนิดนึงนี่เนาะเนี่ยแปลว่าที่ความถี่ตรงตำแหน่งเนี้ยมันเจอเยอะในภาพสปาเชียลในภาพ XY เจอเยอะมากเลยเนี่ยตรงเนี้ย
ที่
ซึ่ง
ความถี่
ใช่ซึ่งมันก็คือไอ้คลื่นนั่นแหละไอ้คลื่นเนี้ยที่เห็นอยู่นั่นแหละเพราะว่าเราใส่เข้าไปมันก็เลยแบบโชว์มาอย่างเด่นเลยอย่างเงี้ยค่ะเป็นความถี่สูงด้วยเพราะเห็นว่ามันเปลี่ยนแบบถี่มากเห็นปะแบบนั้นก็คือสูงประมาณนึง
ความถี่สูง
อืม
อ๋อโอเคครับ
อาจารย์ครับ
ทำไมตรงกลางมันเป็นสีขาวโทษครับ
ตอบไปเร็วเนาะตรงกลางสีขาวเพราะว่าภาพส่วนใหญ่อะจะมี overall information เป็น low frequency เวลาเราเห็นภาพเบอร์นั่นแหละ low frequency หมดเลยค่ะเดี๋ยวให้พาสิทธิ์ถามเลยค่ะ
เราจะรู้ได้ไงว่าในตำแหน่งไหนมันคือค่าความถี่เท่าไหร่เฟสเท่าไหร่
เดี๋ยวอาทิตย์หน้าเราจะมาลองดูกันคืออย่างที่บอกว่ารูปหนึ่งอ่ะการเปลี่ยนแปลงไซน์คอสได้แบบถี่สูงสุดก็คือ2พิกเซลมันก็เลยเหมือนกับ represent ว่าความถี่สูงสุดเนี่ยประมาณ2พิกเซลคือ1คาบเนี่ยความถี่ก็คือแบบ1/2เดี๋ยวอาทิตย์หน้าเดี๋ยวมาดูกันว่าความถี่เนี่ยเราจะรู้ได้ไงว่าตรงเนี้ยมันความถี่เท่าไหร่แล้วเดี๋ยวเราจะแมปเข้ากับสัญญาณไซน์คอสที่อาจารย์ generate ตรงนี้ด้วยค่ะแต่ว่าถ้าเราอยากรู้เราลองไปดูกันก็ได้นะเพราะเราสามารถหาคาบได้จากไซน์คอสถูกปะคาบของมันก็คือแบบ2 พายใช่ปะ t เท่ากับ2 พายส่วนด้วยสัมประสิทธิ์ตรงเนี้ยใช่ไหมซึ่งจะเป็นพายส่วน3อย่างเงี้ยค่ะเพราะฉะนั้นตรงนี้ก็คาบเลยก็จะเท่ากับ6เนี่ย6พิกเซลแบบเนี้ยค่ะพูดเร็วไปปะแต่เดี๋ยวอาทิตย์หน้าได้มาลองดูแน่นอนเนาะในเรื่องของการเทียบความถี่ที่มันโชว์บนสเปกตรัมในฟูเรียเทียบกับแบบความถี่จริงๆที่เป็นพิกเซล
ผมยังสงสัยว่าเราทำ Fourier transform เพื่อจะแสดงภาพออกมาในรูปขององค์ประกอบของไอตัว sine wave ใช่ไหมฮะ
ใช่
ไอที่สงสัยก็คือทำไมถึงจะมีจำนวน sine wave ที่เอามาประกอบกันเท่ากับจำนวนขนาดของภาพทุกครั้งนะครับ
มันเป็นคือตอนที่เราทำ discrete คือจริงอ่ะFourier transform มันมาจาก continuous ใช่ป่ะแบบ infinity เลยแต่พอเอามาแปลงในรูปแบบของ discrete เนี่ยนะอธิบายไงดีล่ะพอมาแปลงในรูปแบบของ discrete อ่ะคือเขามองว่าเดี๋ยวอาจารย์ขอรื้อฟื้นกันนะเขามองว่าในหนึ่งภาพเนี่ยมันก็คือคลื่น1 คาบเลย คือเหมือนจริงๆแล้วมันดีไลฟ์มาจากนึกออกแค่ไซเวฟอะมันเป็นคาบไม่รู้จบแต่พอมาแปลงเป็น discrete อะเราใช้แบบ infinity ไม่ได้เขาก็เลยมองว่า discrete function discrete image เนี่ยก็คือจริงๆแล้วอ่ะคือหนึ่งคาบพิจารณาแค่หนึ่งคาบมันก็เลยว่าพอมันแปลงไปอยู่ frequency domain ใช่ไหมก็พิจารณาที่ไซส์เดียวกันเลยที่ไซส์เดียวกันแล้วก็ยืดหดหรือ normalize ตัว frequency อ่ะไปตามขนาดของตัวรูปภาพหรือว่าพิกเซลอ่ะแต่ความถี่ที่สูงสุดอ่ะความถี่ที่สูงสุดที่เป็นไปได้ก็คือแบบ2 พิกเซลต่อ1คาบoutput size จะเหมือนกันเลยทั้ง frequency แล้วก็ original image อันนี้อยู่อันนี้เราอยู่ปี3ป่ะหรือว่าปี4
ปี4ครับ
ปี4ใช่ป่ะใช่แต่ว่าไซส์มันเท่ากันเดี๋ยวคือจริงๆอ่ะมันมีอยู่ในวิชา เราได้เรียนเลขแล้วใช่ไหมหรือว่าไม่ได้เรียน
เรียนไปแล้วครับ
เรียนไปแล้วใช่ไหมมันอยู่ตอนที่เรากำลังจะแปลงตัว discrete อะให้เป็นดิจิตอลและ in แบบ computation เดี๋ยวจานดูมาให้อีกทีก็ได้จะได้แบบให้เราแบบ ให้เราแบบจำได้หรือฟื้นนะค่ะติดไว้ก่อนนะ
อันนี้ขอถามเพิ่มเติมจากเพื่
ได้
อน
เลย
ก็คือ
ศา
ว่า
สลินถามค่ะ
แปลว่าความถี่มันก็คืออ
ม
ประมาณว่าบอกว่าในกี่พิกเซลเนี่ยมันมีใน
การ
หนึ่งคาบเนี่ยมันมีกี่พิกเซลใช่ไหมฮะแต่ว่าสงสัยว่า
ใช่
ทำไมมันถึงแม็กที่ตรงกลางฮะมันถึงแบบไม่ไปสุดภาพไปเลย
max ที่ตรงกลางไปไม่สุด
แบบ
ภาพ
แบบว่า
อืม
ความถี่ที่มากที่สุดมันคืออยู่ตรงกลาง แต่ถ้าเกิดเลยจากตรงกลางไปแล้ว มันจะน้อยลงอะไรเงี้ยอันนี้คือตอนที่ยังไม่ได้ชิปออริจิน
ใช่คือเดี๋ยวถ้าเราเรียนเลขอ่ะศาสตร์สลินปี3เนาะจำได้ใช่ปะ BG15 ด้วย
ครับ
ใช่ปะเดี๋ยวเราเรียนเลขอ่ะ จะได้เห็นตอนที่มันแปลงฟูเรียร์ทรานส์ฟอร์มจริงๆอ่ะมันครบนะแต่ว่ามันจะมีคอมโพเนนต์ในทางลบด้วยแต่ว่าเราอ่ะทำอิมเมจอ่ะเราจะเห็นแต่ในทางบวกเพราะฉะนั้นไอ้ตรงส่วนลบอ่ะมันก็เลยส่วนกลับมาตรงด้านหน้าด้านหลังอย่างเงี้ยค่ะใช่ปะใช่ด้านหลัง
ครับ
พูดง่ายๆว่าจริงๆมันครบนะแต่ว่าแบบแค่ว่ามันมีค่าลบด้วยเวลาที่เราแปลงฟูเรียร์ทรานส์ฟอร์มจริงๆแล้วมีความถี่ทางลบด้วยอะไรเงี้ยแล้วมันก็ชิปมาเราตัดแค่ตั้งแต่0ขึ้นไปไง
ก็ยังงงอยู่ฮะ
อืม
แต่ก็คือมันเป็นลบใช่ไหมแบบเหมือนว่าอีกด้านหนึ่งมันเป็นลบมันก็เลยแบบว่านับ
ใช่
แค่ครึ่งหนึ่ง
ใช่แต่พูดง่ายๆว่าพูดง่ายๆไม่ได้เดี๋ยว ต้องกลับไปดูกลับไปดูว่าจะต้องเล่าให้เราฟังคือไม่อยากลงในเรื่องของการแบบproof มากเพราะว่ามันเป็นเรื่องมายาวเหมือนกันนะแต่พอไปใช้แล้วมันก็จะมี question เยอะว่าทำไมไซส์มันต้องแบบลิมิตเท่านี้อะไรเงี้ยเนาะแต่ว่านั่นแหละมันอยู่ที่มุมนั้นว่าเวลาที่เราพิจารณามันก็เลยเหมือนกับว่ามันมีความถี่ในทางลบแล้วเราก็เลยแบบทางขวาเนี่ยเราได้มาแค่ครึ่งเดียวจะอธิบายไงดีวะเดี๋ยวขอไปหาวิธีอธิบายนิดนึงแล้วกัน จะได้แบบเข้าใจมากขึ้นนะคะ
ครับไม่เป็นไรฮะ
ได้โอเคแล้วเราถามเรื่อง equivalent ใน convolution theorem ด้วยใช่ปะit can be obtained of the other side by Fourier transform of or inverse Fourier transform right ยังไงนะถามอีกรอบเลยได้ปะ
ประมาณว่าคือว่าคือมันแบบว่าถ้าเกิดคือเหมือนว่ามันเป็นแบบอะไรอะค่าที่ corresponding กันในอีกสเปซหนึ่งอะไรประมาณเนี้ยเราก็สามารถแทนฟอร์มกลับไปมาได้อะไรอย่างนี้
คือฟอร์มมันกลับไปมาด้วยแบบ Fourier transform กับ inverse Fourier transform มันเหมือนเป็นคู่แพร ถ้าอยากจะดูในโดเมนใดโดเมนหนึ่งก็แปลงมันกลับไปอย่างเงี้ยค่ะ
อ๋อครับ
อืมอืมอืม
โอเคฮะแล้วก็พอเก็ตแล้วฮะขอบคุณครับ
ค่ะ แต่ก็สอนเรื่องนี้มาหลายรอบเหมือนกันที่ร้านค่ะ โอเค มีคำถามอะไรอีกไหมมีคำถามอะไรอีกไหม
ใช่ครับยกตัวอย่าง Fourier transform ของรูปต่างๆแล้วแบบอธิบายว่าแบบเรา transform ไปแล้วทำไมมันเป็นเส้นอย่างนั้นนะครับ อย่างควิสที่แล้วอาทิตย์ที่แล้วอย่างเงี้ย
ใช่ใช่
คือ
มีประวัติในอันนี้เดี๋ยวดูก่อน
สงสงสัยเรื่องไอ้กราฟที่เราโชว์เป็นรูปของ
แมวเหมี
ไอ้
ยวอะไรบ้านอะไรอย่างงี้ใช่ไหม
magnitude spectrum เนี่ย
อืมอืม
งงว่าแบบสเปกตรัมมันรีเลทกับรูปยังไงอะแบบถ้าเรามองรูปแล้วเราจะมองสเปกตรัมออกไหม
ใช่เรา
ที่อาจารย์บอก
สามารถ
อาทิตย์ที่แล้วว่าเราจะมอง
ใช่
อย่างเงี้ยครับ อย่างเงี้ยเรามองยังไง
ก็ส่วนใหญ่อ่ะเวลาที่เราหาความถี่ในทิศทางไหนอ่ะมันอืมตัวอย่างเช่นเอารูปที่ง่ายที่สุดเลยเนาะมันจะเป็นรูปอย่างเช่นรูป มันจะเป็นรูปง่ายๆอย่างเงี้ยรูปง่ายๆอย่างเงี้ยเราก็จะเห็นว่ามันมีเส้น1 เส้นใช่ปะแปลว่ามันมีความถี่ในแนวแกนนอน เพราะอะไรเราสามารถที่จะวางไซน์คอสตรงนี้ได้ถูกปะ
ครับ แล้วทำไมมีความถี่แนวนอนครับ
ก็มันมีการเปลี่ยนแปลงของสีไงสีดำไปสีขาว เพราะฉะนั้นเราก็สามารถ represent ได้ว่ามันมีความถี่เป็นรูปคลื่นวาดได้ป่าวะตรงนี้เดี๋ยวขอลองวาดดูอ่าเดี๋ยวลองวาดดูนะอาจจะมองเป็นรูปคลื่นอันนี้สีดำเนาะสีดำก็อาจจะเป็นอย่างเงี้ยอันเนี้ยก็1 ความถี่แหละแล้วความถี่ที่มาเติมเต็มเล็กๆอีกอย่างเงี้ยเพื่อให้มันแบบเป็นสัญญาณแบบนี้ค่ะเพราะฉะนั้นตัวนี้จะมีความถี่แบบที่เป็นอยู่ในแนวค่าแกนนอนตรงนี้ในขณะที่ในแนวแกนตั้งลองดูดิว่าไม่มีการเปลี่ยนแปลงอะไรเลยลากเส้นราวลงมาดำหมดดำหมดดำหมดหรือว่าขาวหมดขาวหมดขาวหมดก็แปลว่าไม่มีความถี่ในแนวแกนนั้นเลยตรงนี้ก็เลยไม่มีสเปกตรัมอะไรใดๆอย่างเงี้ยค่ะ
โอเคครับพอเก็ตแล้วแล้วขอดูมีรูปต่อไปไหมครับ
รูปต่อไปเดี๋ยวขอวางปากกาแป๊บนึงอันนี้ติดอยู่erase ต้องลบ โอเคแป๊บนะคะโอเคเคลียร์แล้วก็ปิดปากกาแล้วก็ลากลงอย่างรูปนี้รูปนี้น่าจะมาจากรูปนี้ถ้ารูปนี้ก็จะมีรูปทางซ้ายเพราะว่ามันมีสามารถวางซ้ายคอร์สได้ในแนวแกนนอนแล้วก็ในแนวแกนตั้งถูกปะ
ครับ
ก็เลยมี2 ด้าน เช่นกันกับรูปนี้น่าจะเป็นรูปที่เป็นเขาเรียกอะไรนะรูปที่มันเป็นแบบเหมือนรูปตัว
เฉียงป่ะครับ
รูปเหมือนคางอะไรนะ4 เหลี่ยมขนมเปียกปูนมั้งก็เลยมีเป็นรูป
อย่าง
แบบ
ขนม
นี้
เปียกปูนคืออะไรอะมันคือรูปไดมอนด์อย่างงี้ป่ะครับ
ใช่อันนี้น่าจะยังไม่ได้รันมั้งแป๊บนึงนะคะรูปนี้มันก็เลยมีวางขึ้นฟูในแนวแกนตั้งในแนวแกนนอนได้ในแนวแกนเอียงใช่
แล้วไอ้
อืม
งั้นไอ้ตัวสเปกตรัมอย่างเงี้ยครับ มันอยู่ใน frequency domain ถูกไหมครับ
ใช่ใช่
ไอ้รูปสีดำๆเนี่ยครับ มันคืออยู่ใน frequency domain
ใช่นี่ frequency แล้ว อันนี้ frequency แล้วเหมือนกัน เดาว่านี้น่าจะยังไม่ได้ดึงล็อกมั้งถ้าจำไม่ผิดจำไม่ได้ละเดี๋ยวดูก่อน โชว์ image ธรรมดา โชว์สเปกตรัมที่ยังไม่ดึงล็อกใช่ค่ะ อันนี้ยังไม่ดึงล็อกแล้วดึงล็อกก็เห็นค่ามากขึ้นค่ะ อืม
เออ
อืม
อ๋อ
พูดง่ายๆว่าสเปกตรัมมันจะโชว์ตั้งฉากกับเส้นในรูปว่างั้นเถอะก็เลยพาลงมาดูไอ้รูปล่างๆที่เป็นรูปบ้านต่างๆเนี่ยสเปกตรัมจะโชว์ตั้งฉากน่าจะดูไม่ชัดแต่อันเนี้ยตรงหลังคามันเนี่ยก็คือเส้นนี้อย่างเงี้ยหลังคานี้ก็คือเส้นนี้อย่างเงี้ยน่าจะใช่นะมันจะโชว์สเปกตรัมตั้งฉาก
แล้วคือไอ้กราฟสเปกตรัมอะครับ กราฟสเปกตรัมอย่างเงี้ย magnitude ของมันคือ strength ของ frequency นั้นๆถูกไหมครับ
ใช่ ใช่ค่ะ
แล้วเพราะฉะนั้นหนึ่งพิกเซลในกราฟอันล่างอะครับ ก็จะ represent 1 frequency เหรอครับ
ใช่1 frequency ใน x and y ด้วยมันอาจจะมีผสมผสานกันที่เป็น u กับ v อะค่ะ
ก็คืออย่างตรงกลางเนี่ยที่บอกว่าเป็น low pass ก็คือ รูปนี้จะเป็นยังไงก็ตามก็คือจะอยู่ตรงกลาง แล้วก็ตรงนั้นก็จะมี1 frequency อย่างเงี้ยครับ คือเหมือนแบบ frequency value ตามแบบ ก็มีค่ากี่เฮิร์ตซ์ก็ว่าไปอย่างเงี้ย
ใช่ใช่จะดูเหมือนก็ได้เดี๋ยวเราจะลองแปลงออกมาดูเป็นจำนวนแบบคาบในความถี่ในแบบต่อพิกเซลอะไรเงี้ยเดี๋ยวอาทิตย์หน้าน่าจะได้ลอง
มันเป็น location ไม่ใช่เหรอ
ใช่แต่ location มันคือ FUV ไง
แล้ว location มันบอกอะไรอะถ้าอย่างนั้น
FUV ใช่ป่ะแล้ว U มันก็คือความถี่ก็คือ F ในแนวแกนอะไรวะในแนวแกนโรใช่ไหมก็คือในแนว horizontal เนี้ยค่ะกับ V ก็คือ F ในแนว vertical เนี่ย
ใช่แต่มันเป็นอย่างเงี้ยครับ แต่ว่ามันแปลกๆว่าครับถ้าอย่างเงี้ยเพราะว่า UV มันเป็น index
ใช่ UV เป็น index แต่ว่าเป็น index แต่ว่าเดี๋ยวเราจะมาแปลงเป็นจำนวนพิกเซลอีกทีหนึ่งจำนวนความถี่อีกทีหนึ่งเพราะว่าอย่างที่บอกว่า index มันได้แต่0จนถึงครึ่งภาพเลยใช่ป่ะซึ่งที่ครึ่งภาพตรงเนี้ยความถี่สูงสุดมันคือ2พิกเซลต่อ1คาบคือการเปลี่ยนแปลงที่เร็วที่สุดคือเปลี่ยนทุกพิกเซลถูกป่ะการเปลี่ยนทุกพิกเซลเพราะฉะนั้นความถี่สูงสุดก็คือ2พิกเซลต่อ1คาบเราสามารถเทียบบัญญัติตารางหาความถี่ในแต่ละจุดได้
อ๋อ
ประมาณนั้น
ก็คือตรงกลางเราแค่ represent ให้มันเป็น frequency ที่ต่ำที่สุดก่อน
ใช่
แล้วเราค่อยเทียบบัญญัติตารางหาเอา
ใช่ถูกต้อง
ผมเข้าใจแล้วทำไมอาจารย์บอกว่า U คือ frequency คือมันเทียบบัญญัติตารางกับ location ครับ
เข้าใจแล้วว่าทำไมทำให้คนงงเพราะว่ามันเป็น index ถูกป่ะแต่อาจารย์แต่อาจารย์จะพูด frequency ตลอดเลยแต่ความจริงแล้วมัน represent ด้วย index ว่ะอะไรเงี้ยอาจจะต้องมองว่าเป็น index ที่เราจะไปเทียบ frequency จริงอีกทีหนึ่งเนาะ
ได้ครับ
โอเคค่ะ
ขอบคุณครับ
ค่ะขอบคุณมากโอเคคนอื่นทำอะไรไหมเอ่ยถ้าเดี๋ยวคำถามที่ติดเดี๋ยวอาทิตย์หน้าเดี๋ยวมาพูดแล้วกันเนาะไม่รู้จะต้องพูดถึงพรูฟเยอะเปล่าเดี๋ยวจะไปลองดูแล้วกันนะคะโอเคถ้าไม่มีก็โอเคเนาะนะคะทุกคนขอบคุณมากที่ตั้งใจฟังเดี๋ยวโพสต์อันนี้ให้ออนไลน์นะคะวันนี้น่าจะประมาณนี้มีคำถามอีกไหมอยากถามอีกไหมไม่มีแล้วเดี๋ยวงั้นเดี๋ยวอาจารย์วางแล้วนะค่ะขอบคุณทุกคนมากเจอกันอีกทีอาทิตย์หน้านะคะขอบคุณทุกคนขอบคุณหยกด้วยนะคะโอเคค่ะงั้นแค่นี้นะสวัสดีค่ะทุกคน
ขอบคุณครับ
ค่ะ